Ever notice how sci-fi always has fusion power right around the corner? Like it's just a given, along with flying cars and teleportation. It's always the future, not quite the present.
Yeah, it's funny how that works.
But today's deep dive, we're going to make that sci-fi future feel a whole lot closer. We're going deep into fusion energy, especially this new reactor, SMART, and all the hurdles we still got to clear to, well, make it a reality.
Sounds exciting.
This isn't just some theoretical dream anymore, though, is it? They're actually building this thing in Spain, brick by magnetic brick, as it were.
That's right, and it's a global effort, too, which is pretty amazing when you think about it.
That's what I think is so cool. It's not just one country going, we're going to crack fusion. It's like the whole world pitching in.
It really is a global collaboration, and it has to be, right? This is a massive undertaking.
Totally. So speaking of global teamwork, our sources mention this place called the Princeton Plasma Physics Laboratory, PPPL for short. They're playing a big part, right?
Absolutely. They've been essential in creating the computer models used to fine-tune SMART's design.
So like a digital blueprint, but for a machine that can, harness the power of the stars.
Exactly. And it's not just about replicating what happens in a star, it's about controlling it. And that's where these computer models are crucial.
How so?
Well, PPPL's modeling helped them crack a specific problem with plasma behavior, predicting and mitigating these little hiccups that used to cause disruptions.
Hiccups. That sounds almost cute for something happening inside a machine trying to fuse atoms.
Right. But those hiccups can be a big deal. They can cause the whole plasma to become unstable, which, well, you don't want in a fusion reactor.
That makes sense.
So yeah, PPPL's work here was huge. It's this kind of international collaboration that's key to, unlocking fusion's potential.
Okay, so we've tossed around plasma a few times now. For those of us who haven't been inside a tokamak lately, what exactly are we talking about here?
Right, good point. Plasma is often called the fourth state of matter. You've got your solids, liquids, gases, and then things get really wild with plasma.
Wild how?
Well, it's basically what happens when you heat a gas so much that the atoms start losing electrons and then they become electrically charged.
Okay, so we're talking crazy high energy here, like hotter than the sun kind of energy.
You got it. The core of the sun. Basically a giant ball of plasma. And to achieve fusion, you need those kinds of extreme temperatures to force those atoms to fuse together and release energy.
So we're talking about containing something with like the energy of a star here.
Yeah, it's a bit of a challenge.
Just a tad. And this is where the smart reactor comes in, right? This is what it's designed to do, hold this superheated plasma. But instead of, some sci-fi force field, it uses magnets.
Exactly. SMART is what's called a tokamak, which basically uses these crazy strong magnetic fields to contain and control the plasma.
So like trying to contain an explosion with invisible forces.
Pretty much. That's a good way to think about it.
And I'm guessing that's where things get really, really tricky, right? I mean, containing an explosion is hard enough, but we're talking about an explosion that's hotter than the sun, and we need it to, last long enough to actually get usable energy out of it?
Yeah, you've hit the nail on the head. One of the biggest hurdles in fusion research has always been, maintaining that stable confinement. Plasma, you see, is not exactly known for being well-behaved.
It's a bit of a diva, you're saying.
Something like that. Even the slightest fluctuation can cause it to wobble and, crash into the reactor walls, which is not good.
Not good at all, I imagine.
Yeah.
For the reactor or anyone standing nearby.
Definitely not. A major disruption like that, it can damage the reactor itself, mean costly repairs, downtime. Not ideal. That's actually one reason why the modeling work PPPL did on SMART is so important. They've made some serious strides in predicting and mitigating those instabilities, which makes the whole operation safer and way more efficient.
That makes a lot of sense. Okay, so let's say we've got this super hot, super unstable plasma, all bottled up nice and safe. What happens next? How do we actually get usable energy from it?
Okay, so that's where the fusion and fusion energy really happens. When those atoms in the plasma, remember they're superheated? Well, when they're squeezed together under all that pressure, they fuse. And when they fuse, boom, they release this tremendous amount of energy.
My brain is kind of melting just trying to picture it. So we're really talking about recreating the process that powers the sun, but like here on Earth, inside a machine.
It's pretty wild when you think about it like that.
It really is. But it's not just the heat and pressure that's mind-boggling, is it? What about those neutrons we talked about earlier?
Ah, yes, those. You don't forget, do you?
Tiny atom-smashing bullets. Hard to forget something like that.
Well, when fusion happens, you get a whole bunch of these high-energy neutrons released, and they're actually key to generating power in a fusion reactor, BUT.
Always a but, isn't there?
There usually is, unfortunately. The thing about neutrons is that, well, they don't really play nice with matter. It's like a constant barrage of microscopic bullets bombarding the reactor walls. That's what we're dealing with. And over time, this neutron bombardment, we call it neutron damage, it degrades the reactor materials, makes them brittle, radioactive, not good.
So it's not just the heat, it's also this constant microscopic bombardment that makes fusion such a challenge.
Exactly. And that's a big reason why material science is such a huge area of research in the fusion world. We need to find materials that can withstand these insane conditions. It's like trying to find something that's both fireproof and bulletproof.
Yeah, good luck finding that on Amazon. Okay, so we've got the plasma confinement challenge, we've got the material science hurdle. Anything else standing between us and a fusion-powered future?
Well, there is one more big one, arguably the most important of all, actually, and it all comes down to...
Okay, let's talk money then. Because containing something as hot and energetic as the sun, finding materials that won't, disintegrate, it's got to be expensive, right?
It's the million-dollar question, literally. I mean, right now we're pouring tons of energy in just to get these reactions going.
Right.
And we're not exactly getting enough energy out to make it, worthwhile. Yeah.
So it's like pouring a whole tank of gas into your car just to drive down the driveway and back?
That's a pretty good analogy. The holy grail of fusion research is achieving what's called ignition. That's when the fusion reaction actually becomes self-sustaining, producing more energy than it consumes.
Right. Which kind of makes sense, right? If we're talking about this as an energy source, it can't just be a giant energy black hole.
Exactly.
But what are the chances, realistically, of us actually getting there? I mean, this all sounds, well, expensive to say the least. Is it realistic to think that fusion could really become a viable source of energy? Or is this just, a scientific pipe dream?
It's a fair question, and there's no easy answer, but here's the thing, the potential payoff, it's enormous.
Okay, how so?
If, and it's a big if, but if we can crack the code on fusion, we'd have a practically limitless source of clean energy. No greenhouse gases, no long-lived radioactive waste like you get with fission. It'd be huge.
So a game changer, not just for our energy needs, but for, the planet as a whole.
Exactly.
Okay. But even if the science actually works out, aren't we still talking about decades of research and development? Billions, maybe even trillions of dollars?
Yeah, it's a serious investment, for sure, no doubt about it. But think about it this way for a second. Early computers, they were massive, super expensive. Right?
Oh, yeah. Only governments and, giant universities could even dream of having one.
Exactly. And now we walk around with more computing power in our pockets than those early computers could ever imagine.
It's true. I mean, my phone can barely make it through the day without needing a recharge, but it's still pretty amazing when you think that way.
Right. So it's about playing the long game.
So with fusion, we need to, kind of think long term. Take that same approach.
Yeah, I think so. Because it's not just a scientific endeavor at this point, it's societal.
That's a really good point, because you've also got all the geopolitical stuff too, right?
Absolutely.
I mean, if one country, or even a group of countries, manages to crack fusion, it totally changes everything, doesn't it?
Completely. We're not just talking energy independence either. We're talking a whole new energy paradigm.
It's kind of mind-blowing, isn't it?
It really is.
It almost makes you wonder if we're, on the verge of a new kind of space race. Not to the moon this time, but towards a fusion-powered future.
No, that is an interesting thought. And it's something worth thinking about, as we explore this whole new frontier of science and technology.
Absolutely. Well, on that note, that's all the time we have for today's deep dive into fusion energy. We covered a lot, didn't we? From the inner workings of a tokamak to the geopolitical implications of a fusion-powered future. It's complicated.
It is. It's a lot.
But one thing's clear, I think. Fusion has the potential to change everything. So, to our listeners, stay curious, keep asking questions, and who knows, maybe one day we'll all be driving those fusion-powered flying cars. Thanks for joining us.